Late on a Sunday night, without any warning at all, the ocean floor off the coast of Vancouver Island suddenly lurched. A magnitude 5.6 earthquake tore through the seabed, and within seconds, the shaking had traveled hundreds of kilometers in every direction. People felt it on northern Vancouver Island. People felt it in Victoria. People felt it clear across the water in Seattle, Bellingham, and Port Townsend. For most residents, it was over in moments, a strange rattle, maybe a picture frame shifting on the wall, then silence. But for the scientists who study this specific stretch of coastline for a living, that quake was not just a passing curiosity. It was a data point, one more piece of evidence, in an ongoing, deeply consequential effort to understand one of the most dangerous fault systems on the entire planet, sitting quietly just offshore from millions of people who mostly have no idea it is even there. Let's start with exactly what happened, because the basic facts here are already confirmed and worth understanding clearly. According to Earthquakes Canada, the quake struck at 11:41 at night on Sunday, roughly 219 kilometers southwest of Port Hardy, near the northern tip of Vancouver Island. It occurred about 10 kilometers beneath the ocean floor, a relatively shallow depth for an earthquake of this size, which is part of why the shaking was felt so widely across such a large area. The epicenter sat far from any major population center, roughly 300 kilometers from Campbell River and 330 kilometers from Port Alberni, and the earthquake was still strong enough to be felt in Metro Vancouver, more than 450 kilometers away. Authorities were clear and quick about one specific point. There was no tsunami risk from this particular event, and no injuries or property damage were reported anywhere along the coast. In other words, this was a genuinely significant earthquake by any normal measure, but it passed without causing real harm, which is exactly the kind of outcome that lets scientists study it carefully rather than simply respond to a disaster. So why does an earthquake that caused no damage and posed no tsunami threat deserve this much attention at all? The answer has almost nothing to do with this specific quake in isolation and everything to do with where it happened. The stretch of the Pacific Northwest coastline, running from Northern California up through Oregon, Washington, and British Columbia, sits directly above something called the Cascadia Subduction Zone, a massive fault system where one of the Earth's oceanic plates, the Juan de Fuca plate, is slowly, continuously being forced underneath the much larger North American plate. That kind of collision between two tectonic plates is exactly the same basic setup that produced the catastrophic 2011 earthquake and tsunami in Japan, and the devastating 2004 earthquake and tsunami in the Indian Ocean. Subduction zones like this one are capable of producing what scientists call Megathrust earthquakes, among the largest and most destructive earthquakes that occur anywhere on Earth. Here's the detail that should genuinely get your attention. Scientists already know Cascadia is capable of producing an earthquake in the range of magnitude 9, an almost unimaginably powerful event compared to the 5.6 that rattled Vancouver Island this past weekend. And they know this not from speculation, but from careful geological detective work. Researchers have found physical evidence in soil layers, in coastal sediment, in old written accounts from Japan describing a mysterious tsunami with no local earthquake to explain it, all pointing to the same conclusion. The last time Cascadia ruptured fully was in January of 1700, more than 300 years ago. That earthquake was powerful enough to send a tsunami all the way across the Pacific Ocean to Japan, arriving with enough force that Japanese records from that era describe the wave in detail, even though nobody in Japan felt any shaking beforehand to explain where it came from. It took modern geologists piecing together evidence on both sides of the ocean to finally connect that mysterious tsunami back to a massive earthquake on the other side of the Pacific. That single historical event tells scientists two important things. First, Cascadia is absolutely capable of producing an earthquake at that catastrophic scale. Second, based on geological evidence stretching back roughly 10,000 years, this kind of full rupture appears to happen on a rough cycle, occurring somewhere in the range of every 300 to 500 years or so, though the exact spacing between events has varied considerably throughout that longer geological record. Do the simple math on that cycle, and you arrive at an uncomfortable realization. It has already been more than 325 years since the last major Cascadia earthquake, meaning the region sits somewhere within, or arguably already past, the typical window scientists associate with the fault's recurrence pattern. This is exactly why official risk estimates for this region carry the specific weight that they do. The United States Geological Survey has estimated somewhere around a 10 to 15% chance of a full Cascadia rupture, an earthquake potentially exceeding magnitude 9, occurring sometime within the next 50 years. Oregon's own State Emergency Management Office cites a slightly different, broader figure, estimating roughly a 37% chance of a magnitude 7.1 or greater earthquake somewhere along this fault system within that same 50-year window. Different numbers because they are measuring somewhat different scenarios, but the underlying message from both estimates points in the same direction. This is not a distant theoretical risk confined to textbooks and academic papers. It is a genuinely active, statistically meaningful possibility that emergency planners across the entire Pacific Northwest are actively preparing for right now. If you find this kind of careful look at the science behind the headlines genuinely useful, go ahead and hit that like button. It really does help this channel reach more people who want the full picture, rather than just a scary headline. And if you want to keep following how scientists continue tracking this exact fault system, subscribe, because this is clearly an ongoing story, not a one-time event. It is also worth understanding something genuinely strange about the Cascadia Subduction Zone specifically, something that makes it considerably harder for scientists to study than many other dangerous fault systems around the world. Unlike most subduction zones, which tend to produce a steady, ongoing background hum of smaller earthquakes as the two plates grind past each other, Cascadia is unusually quiet. The plates appear to be locked tightly together by friction, storing up enormous amounts of built-up stress rather than releasing it gradually through smaller, more frequent quakes. That quietness is not reassuring. It is actually part of what makes the fault so difficult to read. A fault that stays locked and silent for centuries is simply accumulating strain the entire time. And when it does eventually break, that stored energy releases all at once rather than in smaller, more manageable increments. That specific challenge, trying to understand a fault that mostly refuses to give scientists any warning signs, has driven a wave of genuinely fascinating recent research. Earlier this year, researchers at the University of Washington published findings describing something they called fluid highways, running through the fault itself, essentially channels where fluid migrates through the rock and appears to influence how stress builds and releases along different sections of the subduction zone. Understanding those fluid pathways in more detail could eventually help scientists better predict not just whether Cascadia will rupture, but how a rupture might actually spread once it begins, which sections might break together, which might remain more isolated. Separately, other researchers examining data from an ambitious offshore survey called the Cascadia Seismic Imaging Experiment found something else worth understanding. Evidence that part of the tectonic plate feeding into this subduction zone actually appears to be tearing apart deep underwater, with one large section of oceanic plate having dropped by more than 3 miles compared to the surrounding rock. Some scientists have described this as catching a subduction zone in the act of slowly dying, a genuinely rare thing to actually observe directly. But other researchers studying that same finding have been careful to add an important caution. A tear like this might influence exactly where a future earthquake rupture starts or stops, or how far it travels once it begins, but it absolutely does not eliminate the underlying seismic hazard the fault still poses. In plain terms, this specific corner of the fault might be behaving in an unusual way, but the broader system remains just as capable of producing a massive earthquake as it always has been. There's also a genuinely sobering angle here connecting Cascadia to an entirely separate fault system that most Americans have heard of far more often, the San Andreas Fault running through California. Research published earlier this year suggested these two massive fault systems, long treated by most people as separate, unrelated hazards, may actually be more connected than scientists previously realized, raising the unsettling possibility that a major Cascadia rupture could potentially influence stress along the San Andreas as well, or vice versa. That kind of research remains genuinely early and far from settled, but it illustrates exactly why a single moderate earthquake off Vancouver Island draws this much scientific attention. Every new data point, every fresh set of measurements from an event like this past weekend's quake, feeds directly into models that scientists are still actively refining, models trying to answer some of the most consequential open questions in earthquake science anywhere in North America. It is worth being clear and honest about one thing before we go any further, because responsible coverage of this topic requires it. This past weekend's magnitude 5.6 earthquake was almost certainly not directly on the Megathrust fault itself, the specific boundary where the Juan de Fuca plate slides beneath the North American plate. Earthquakes in this general offshore region, including several previous moderate quakes over the past few decades in a similar location, are more commonly associated with a separate structure called the Nootka Fault Zone, a transform boundary where a smaller tectonic plate meets the Juan de Fuca plate at an angle, producing its own pattern of moderate earthquakes distinct from the main subduction zone itself. That distinction matters because it means this specific earthquake, while genuinely significant and genuinely felt across a wide area, is not itself direct evidence that the larger megathrust fault is about to rupture. It is a separate, though geologically related, seismic feature in the same general neighborhood. That distinction is exactly the kind of nuance that responsible science communication has to include, rather than letting every earthquake near a dangerous fault get automatically framed as a sign the big one is imminent. Scientists studying this region are careful to note that no one currently has a reliable way to predict exactly when a major Cascadia rupture will occur, whether that is next year or in another 100 years. What earthquakes like this past weekend's event actually provide is something more useful and more modest than a prediction. They provide fresh seismic data, fresh opportunities to test instruments, and fresh reminders for both scientists and the public that this fault system remains active and worth taking seriously, even when any individual earthquake itself causes no damage at all. This is also exactly why so much current research effort and public investment continues flowing into simply improving our basic understanding of Cascadia. Hawaii University of Washington received more than $10 million back in 2023 specifically to build an underwater observatory directly on the subduction zone, aiming to gather far more direct, continuous data than the historically sparse, mostly onshore measurements scientists have had to rely on for decades, because so much of this fault sits miles offshore, deep underwater. It has always been considerably harder to study directly compared to fault systems that run through accessible, easily instrumented land. Every new sensor, every new offshore survey, and yes, every earthquake like this past weekend's event adds another small piece to a puzzle that remains, in many important respects, still only partially understood. So what should you actually take away from all of this, now that we have walked through exactly what happened off Vancouver Island and exactly why scientists care so much about it? The honest, balanced answer holds two things together at once. This past weekend's earthquake on its own was a moderate, non-destructive seismic event, felt widely but causing no real damage, and it does not represent direct evidence that a catastrophic Cascadia rupture is imminent. But it occurred in one of the most geologically significant, most carefully monitored corners of North America, precisely because the broader Cascadia Subduction Zone genuinely is capable of producing a devastating magnitude 9 earthquake, has done so before within recorded and geological history, and sits within a time frame where credible scientific estimates place real, non-trivial odds on that happening again within the coming decades. Millions of people live directly above a fault system that remains only partially understood, studied in fits and starts through offshore surveys, underwater observatories, and occasionally through smaller earthquakes just like this one, each of them offering scientists one more fragment of evidence in an investigation that has been quietly unfolding for decades and shows no signs of concluding anytime soon.